Okay, where we left off last time was I was about to do a comparison between the different temperature scales and several, commonly encountered temperatures, or commonly worked with temperatures in the case of absolute zero. For the freezing point of water, we know that that's 32 degrees Fahrenheit, and that's also 0 degrees Celsius. That's how, one of the defining points of the Celsius system. Kelvin is based on the Celsius system. A temperature in Kelvin is equal to the temperature in Celsius plus 273. So the freezing point of water in Kelvin would be 273. And the temperature in Rankine is the Fahrenheit temperature plus 460. So if you take 32 plus 460, you get 492. For the boiling point of water, we know that in Fahrenheit, that's 212. And in Celsius, it's 100, because that's part of the way that, that the Celsius system was set up. Kelvin would be Celsius plus 273, so the boiling point of water is 373. And in Rankine, the boiling point of water would be 212 plus 460. So you're beginning to see why we don't use the Rankine system in math and science. And 212 plus 460 comes out to 672. Now, something that might be interesting for future reference would be to look at the difference between the freezing point and boiling point of water, because it's the same phenomenon no matter how you're measuring it. So it could be instructive to look at what the difference in temperatures is between the freezing and boiling point of water on different temperature scales. Okay, so the difference between 212 and 32 would be 180 degrees. And obviously the difference between 100 and 0 is 100 degrees. Difference between 373 and 273 is 100. This points up something that can be useful for future reference, and that is that while individual temperatures are different in Celsius and Kelvin, temperature changes or differences in temperatures are actually the same in Celsius and Kelvin, because each degree is the same size in Celsius and Kelvin. The difference between 672 and 492, though, is 180. And that's the same as the difference in Fahrenheit. And that makes sense because Rankine is just Fahrenheit plus a number, and Kelvin is just Celsius plus a number. So the differences actually should be the same in Kelvin and Celsius and in Rankine and Fahrenheit. For room temperature, there's some disagreement. There's room for disagreement anyway on what room temperature should be. Probably know that if you've ever spent a lot of time visiting your grandparents. But we'll say that room temperature is about 70 degrees. In Celsius, that would be equivalent to about 21 degrees. And in Kelvin, 21 plus 273 would be about 294. And in Rankine, that would be 530. So 70 plus 460. The human body temperature, in Fahrenheit, averages 98.6 degrees Fahrenheit. In Celsius, that works out to 37 degrees. And in Kelvin, 37 plus 273 is 307. And in Rankine, it's 559. And then absolute zero, of course, is 0 in Kelvin and Rankine. In Fahrenheit, it's minus 460 degrees. And in Celsius, it's minus 273. And so you don't have to know all of these different temperatures. You should be able to convert one into another, though. That's something that we might see on tests or quizzes. These are the conversions between Celsius and its corresponding absolute temperature scale, and Fahrenheit and its corresponding absolute temperature scale. We also need to be able to convert between Fahrenheit and Celsius. In order to do that, you have to convert, you have to compensate for two different things. In converting from Fahrenheit to Celsius, you have to compensate for the fact that they start at different 0 points. 0 Celsius corresponds to 32 Fahrenheit. You have to compensate for that. And you also have to compensate for the different size of each degree. If you look at the difference between the boiling point and freezing point of water, you'll see it in action. 100-degree difference in Celsius is 180-degree difference in Fahrenheit. And so what that means is that each Celsius degree is about 1.8 degrees Fahrenheit. And you can get that just by taking 180 divided by 100, 1.8. So 100 degrees Celsius, or each 100 degrees Celsius is equivalent to 180 degrees Fahrenheit. And that means that each degree Celsius is equivalent to 1.8 degrees Fahrenheit. All right, so when we want a temperature in Fahrenheit from Celsius, the temperature in Fahrenheit would be 1.8 times the temperature in Celsius plus 32. Okay, that makes more sense now. The 1.8 is for compensating for the different size of each degree, and the 32 compensates for the different 0 points. Temperature in Celsius is just temperature in Fahrenheit minus 32 over 1.8. And again, 32 is to compensate for the different 0 points, and 1.8 compensates for the different size of each temperature. Also, oh yeah, from up here, if you want to go from Kelvin to Fahrenheit, or to Celsius rather, temperature in Celsius is temperature in Kelvin minus 273. And I'm not going to show the other way because who cares about Fahrenheit? So as an example, we can convert 65 degrees Fahrenheit to degrees Celsius. Now, 65 degrees Fahrenheit is just a little below room temperature. So we would expect the temperature in Celsius to be a little bit under 21. So we'll keep that in mind as we find our answer. Okay, so we want temperature in Celsius. That's temperature in Fahrenheit minus 32 over 1.8. That's 65 minus 32 over 1.8. 65 minus 32 is 33 over 1.8. And let's see, 33 divided by 1.8 is 18.3 repeating degrees Celsius in two significant figures, because that's what we had for all of these temperatures. Well, you could consider 32.0 to be an exact number, but the 1.8 is only two significant figures, and the 65 was only two significant figures. So we'll call that 18 degrees Celsius. So you can also convert something like negative 25 degrees Fahrenheit to Celsius. Negative temperatures are something you have to watch out for because it's easy to get mixed up with all the negative signs. So doing this, let's see, temperature in Fahrenheit is negative 25. Temperature in Celsius will be negative 25 minus 32 over 1.8. And that means that's negative 57 over 1.8. And that works out to negative 31.92, but we'll round that to two significant figures. And negative 32 degrees Celsius. How about if you want to convert negative 32 Celsius to Fahrenheit? Not something that we'd actually want to do very often in this class, but say it's really, really cold day over in Canada and they report the temperature, but it's in Celsius, so you want to sort of relate to it. You want to know what it is in Fahrenheit. So now you can actually convert it to Fahrenheit. Temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. So that's 1.8 times negative 32 plus 32. Let's see, negative 32 times 1.8 is negative 57.6 plus 32. And that is negative 25.6 degrees Fahrenheit. And say, what if you wanted to convert negative 32 degrees Celsius to kelvins? Well, the temperature in Kelvin is the temperature in Celsius, which is minus 32 plus 273. And minus 32 plus 273 is 241. Okay, no degree sign. And so what if you wanted to convert negative 182 Celsius to Fahrenheit? And feel free to stop at any point and stop the video and try it yourself and see if your answer measures up to mine, or agrees with mine. Temperature in Fahrenheit is 1.8 temperature in Celsius plus 32. And that is equal to 1.8 times 182 plus 32. And 1.8 times 182 is 327.6 plus 32 gives us 359.6. And let's see, we had three significant figures. That's approximate though, so that's only 2. So 360 without the decimal point would be our answer. Okay, I'm going to switch this one around just because who really cares about going to Fahrenheit? We're scientists, we use Celsius now. So convert negative 75 Fahrenheit to Celsius. Well, we have temperature in Celsius is equal to Temperature in Fahrenheit minus 32 over 1.8. Temperature in Fahrenheit is negative 75 minus 32 over 1.8. Okay, so negative 75 minus 32 is negative 107 over 1.8. And we get negative 59.4, yeah, two significant figures, so we'll call that negative 59 degrees Celsius. So what if you want to convert 657 Kelvin to degrees Celsius? Well, temperature in Celsius is temperature in Kelvin minus 273. So 657 minus 273 would be 384 degrees Celsius. An interesting exercise. Would be, if you're wondering, the Celsius and Fahrenheit temperature scales cross at a certain point. At temperatures above 0, the Fahrenheit temperature is higher than the Celsius temperature. And if you go below 0, it stays that way for a while, but eventually it crosses over to the point where the Celsius temperatures are higher numerically than the Fahrenheit temperature. And so we can actually use algebra to figure out where that crossover point is. You know, at what temperature, basically at what point are the Celsius and Fahrenheit temperatures the same as each other? So we're going to let X be that temperature. And all we have to do is basically put X into the formula for converting Fahrenheit to Celsius and Celsius to Fahrenheit and make them equal to each other. Okay, so changing Celsius to Fahrenheit, it's 1.8 times the temperature in Celsius plus 32. So we're going to represent temperature in Celsius as X. And going the other way, it's temperature in Celsius is equal to temperature in Fahrenheit, which we're going to call X, minus 32 over 1.8. And so now all we have to do is solve for X. Yeah, famous last words, I know. So what you have to do in this case is pick one of the two X's, or basically get both of the X's on the same side of the equation and all of the numbers on the other side. That's how you solve for X. So let's see. Let's get the numbers over here first on the left-hand side, and then we can work on moving that X over here. Oh no, actually it might, no, okay, let's do that first. Okay, the right-hand side is divided by 1.8. So if you just multiply everything on the right-hand side by 1.8, that crosses that out. And then we have x minus 32. If you add 32 to both sides, oops, plus 32, then that should get rid of that. Okay, so now we have one of the x's alone. All we have to do is work this out and get the other x over there. So let's see, 1.8 times 1.8 is 3.24. So that's 3.24x plus 1.8 times 32. That's plus 57.6 plus 32 equals x. 57.6 plus 32 is 89.6. And then we can subtract 3.24 x from each side. That cancels this out, so we have 89.6 equals x minus 3.24x. That's 89.6 equals negative 2.24x. And basically, if you take 89.6 divided by minus 2.24, you get x. And that would be minus 40. Minus 40 is where the two temperatures are the same. So minus 40 Fahrenheit is minus 40 Celsius. Okay, so that's what science geeks do for fun. Okay. So now we come to the subject of heat. And heat is a form of energy transfer between two objects. Okay, we have related to heat the concept of external energy. And external energy is the total of potential energy and kinetic energy of an everyday sized object. So we're not talking like protons or neutrons or things like that here. The internal energy is the total potential and kinetic energy of the molecules in an object. And when external energy is transformed into internal energy, the result is a temperature increase. And so looking at heat versus temperature, temperature actually is the measure of the degree of hotness or coldness of an object. And it's really a measure of the average kinetic energy of the molecules. And basically, the warmer the object is, the faster the molecules vibrate and the higher the temperature is. Heat is based on the total internal energy of the molecules. Okay, so for example, if you have two containers of water, and this one is 1 liter, and you have another one that's also filled with water, but it's only 250 milliliters. And each of them is at 90 degrees Celsius, or any other temperature you might want to pick. They have the same temperature, but yet this one, the bigger one, has more molecules and therefore more heat energy. Having the same temperature means that each molecule has the same average kinetic energy, but the bigger container has more molecules in it. So it has more heat energy, which is basically the total energy present, than the smaller one. If you try to cool down the containers of water, or just put it on the counter and wait for it to come down to room temperature, unsurprisingly, the bigger one is going to take a lot longer. And that's because it has more total energy, because cooling it down means removing energy from all of the molecules in it. Okay. Okay, and so more heat energy means more internal energy also. Okay, let's see, heat flow. Okay, I'm going to leave the next topic for the next lecture. So we'll stop right there for now, and I'll see you next time.